Welcome back to compiler construction. So in our previous lectures we were concerned with syntax, and in this lecture now we're talking about things that are beyond syntax. So especially if some data flow works actually that we define in our program. So when we assign elements to other elements in our program, if this actually fits together, and how we can build structures to actually check this in our compiler. So attribute grammars are one way to do this. So first we'll talk about type systems and type checking, and afterwards we'll discuss syntax-directed translation and the related attribute grammars today. So why do we need type systems? So type systems can specify the behavior of a program on a level that's more precise than what we can do in a context-free grammar. So we've seen in a context-free grammar we were unable to check, for example, if we tried to assign like a character to an integer variable or something, because that is something that's outside of this context-free class of languages. And we've also seen that any languages that actually manage to consider this context take much more effort to parse and understand for the compiler. So we want to add something to our compiler in a separate stage that actually allows us to check for things like type compatibility. So here type systems create an additional vocabulary in our language, so a second way to describe the correctness of program. And using this type system approach we can describe both the form and the behavior of valid programs. And type systems provide information that cannot be obtained using the techniques of scanning and parsing we have looked at so far. Why do we need this? Now, of course, safety and security also are very important topics nowadays, especially since so many security problems are out there. And of course, we want our computers to run reliably. So we would assume that when we try to assign one data type to a different one, that there is some problem in our program unless the programmer explicitly tries to do a conversion. So if we do it accidentally, we might lose precision, because if we want to assign, for example, a 32-bit integer to a 16-bit integer, what might happen is that we just lose the correct values for any number that doesn't fit into 16 bits. We also want to improve the expressiveness of our language, so we want to be able to really create type systems that can enable the programmer in turn to model the real world, so whatever application the programmer is building better, instead of having to rely just on very simple type systems of having like integers, characters, and something like that. And finally, if we know our types are correct and compatible in our program, we don't need to check that at runtime. So if our compiler can check that, we can improve runtime efficiency of our program by reducing the overhead our compiler has to perform when the program is running. So what our compiler should try to achieve is that our program is type safe. So type safety means that our compiler ensures that the results or parts of assignments and expressions are compatible with each other. So if we provide types for data objects and rules for type inference, we can help the compiler with this. Of course, you might have also seen programming languages where you don't need to declare any types of variables. So common languages for these are JavaScript or Python, where there is some sort of automatic type inference happening, but this can also go wrong in quite spectacular ways. So what are the other alternatives to type safety? Well, there's a way to do untyped languages. So assembly is an untyped language because assembler usually only operates on the machine data types that are provided, and machine data types are for most processors more or less just strings of bits, like a 32-bit string, but the processor maybe doesn't even know if the 32-bit number it's handling, if it's actually a pointer or a signed integer or an unsigned integer. There were other early languages that were untyped or only had a single data type, like BCPL, the Basic Combined Programming Language, which was one of the predecessors of C. And BCPL actually only had one data type, a 16-bit integer, which was quite restricting, especially if we wanted to use it for character processing so for example for writing compilers. And there are other weakly typed languages which allow you to do all sorts of type errors. On the other hand, there are also ideas to implement typing or a sort of type system on the assembly language level, and we've given you a reference for this here. So, of course, the CPU still doesn't understand it, but by providing some typed assembly language, we might also be able to check types on a lower level of representation and even do optimizations on this. So, when we want to ensure type safety, our compiler has to perform what we call type checking. So our compiler must analyze the program and it must assign a type to each name and to each expression. So for some programming languages we've seen, the programmer is responsible for assigning a type to each name, like by declaring a variable. And for the expressions, the compiler must figure it out. So it must look at the components of an expression, like immediate numbers, like integers or floating point numbers, or the types of variables that are part of an expression, and then of course which operators combine those, and then the compiler can apply rules to check if all these components of an expression are compatible. And finally, if we could also assign the result of the expression, so the so-called right-hand side, to what's called the left-hand side, so a variable that should contain the result of an expression. So our compiler must check the types to ensure they're used only in legal contexts. But unfortunately, this type checking is a bit of a misnomer because it combines a number of concepts, especially two activities. One activity is type inference. So type inference also takes place for languages where you have to declare variables with types, because you do an inference on expressions using variables and constants. And the other task for type checking is to identify any errors that are related to typing. So type safety is a great way to make your programs more safe and secure to execute. And it might also make your programs faster because you can omit a number of runtime checks. But unfortunately, type safety can also make the life of a programmer harder. And one specific example for this is Niklaus Wirth's Pascal programming language, at least in his original versions. So Pascal has a very strict type system. So Wirth is one of the researchers who is really a proponent of strong typing and strong type checking. Now, Pascal actually goes that far that it also includes the size of an array as part of the data type. So if you declare two arrays in Pascal here, so an array which we call array10, which holds 10 integers, and in Pascal you can specify the range of the array index, so we can say it can run from index 1 to 10. And you declare another array, array20 here, which holds 20 integers. Then obviously you have two different arrays with different sizes. Now the problem is that if you want to write a procedure that handles arbitrary arrays of integers, this doesn't work in Pascal. So you can't really write a procedure like sort that sorts your integer array, because array10 and array20 have different types. So you cannot declare a function that actually takes an array of arbitrary size in standard Pascal. So if you can't write it, you would have to need functions for each variant of arrays, even if they're all on the same base type, that occur in your program. And that's, of course, pretty much problematic, because that causes lots of overhead. But it gets even worse with standard Pascal, because strings in Pascal are declared as arrays of character. So similar to C, but actually in a bit of a different way. So consider that we want to write a function index that takes two parameters, a string and a character. And this function should just return, if it's available, the index of this character C inside of the string we passed. So the first occurrence of the character C inside of the string S, or if character C is not part of a string S, we should just return a 0. So the problem here is, how can we handle the string argument of index? Because we ideally would simply have calls like this: index, then pass a string of 5 characters hello and the character we're looking for, and also index passing a string of 7 characters goodbye and this character we're looking for. Now problematic is that this is a 5-string character, this is a 7-string character, so this is an array of 5 characters. That one is represented as an array of 7 characters, so they are incompatible types. So one of these calls at least cannot be legal, since the strings have different length. So, well, what you can do is a hack. So you could try to declare a common type of string, which is, for example, an array of 10 characters here, and use this variable here to call index, which then is configured to exactly receive a 10-character long string. So the idea would be that if you had such a string of 10 characters, you could assign a string to this variable here, which is essentially an array. Now, unfortunately, this also doesn't work, because the compiler complains about this assignment to temp, because that string on the right-hand side here is obviously a string of 5 characters, and we were trying to assign it to a string variable that holds 10 characters, so it doesn't work because hello and temp have different lengths. Oh my goodness. In addition, of course, you would probably waste a lot of memory space, because if all your strings are shorter, well, you have unused space here. Or if you have a longer string, well, maybe later in the evolution of your program, you would need to adapt all the declarations to also fit the longer string. That's not a good idea, I suppose. Now, of course, programmers wanted to use strings of different lengths in Pascal, obviously. So what were the practical solutions? So the first one was we could try to define a family of routines with a member for each possible string size. So we have something like index 1, index 2, index 3, index 4, index 5. Yes, not a good idea, especially since strings can, in standard Pascal, be up to 255 characters long, and you don't want to write 255 different variables of your functions. And things like templates, which you might know from C++, or generics from Java, or now also available in Go, for example, didn't exist in Pascal, so you would have to write 255 distinctive copies of your function. Or you would need to write a generator for this. Both is not a good idea. So what people actually did in practice is they defined all strings like we've seen before, including constant strings that were used in a program, to have the same length. And that was used in practice, so the example shown below here is actually an excerpt from Word's Pascal compiler source code. And what you see here is that we obviously have symbol lengths here of a number of characters here. And if our symbol that we want to detect is actually shorter than our string length, then we have to pad it with the exact right number of spaces to achieve the result that all of our strings we might assign to this data type here, so an array of strings, has the same length. Well, this wastes a lot of memory, especially it wasted a lot of memory on the very small and simple machines Pascal was developed on in the early 1970s. So that's definitely a definite disadvantage of very strict type checking. But on the other hand, you won't run into problems like C strings, where if you forget the terminating 0, or if you write beyond the end of your string buffer, then you get into lots of trouble with security problems and buffer overflows. So we already mentioned that another advantage of having type systems and types in general is that they allow to specify the behavior of a program more precisely than what would be possible with just context-free rules. And one example for this is operator overloading. So operator overloading means we have an operator like a plus operator here, and depending on the data types that you use, this plus operator can have different meanings. So you have context-dependent meanings for an operator here, which our context-free grammar actually cannot figure out. We've seen this already when we had a look at different grammars and examples here. So, for example, we can have this plus operator, and we can have it for different data types like integers, floats, doubles, and strings. Now, for integers, floats, and doubles, at least the semantics is relatively identical. We want to add two values and have the result stored somewhere. But of course, if you look at machine code that's generated, usually the addition operations for integers are different to the addition operations for float and double variables. So our compiler would have to generate different machine instructions depending on the fact that the parameter was either integer, float, or double. So if we have this example program here, just having integers, so we have three integer variables, x and y, which we initialize to 1 and 2, and the third one, z, for the result. Z equals x plus y we would actually expect our compiler to generate an integer addition and machine instruction, and of course the result should be the integer number 3. Now we have this declaration here, so we use double variables x and y, which have fractions after the decimal point. Now if we add these two together, we would expect our compiler to generate a floating point addition instruction here for double floating points, and the result should be something like 3.5. Now what happens if we actually pass two strings to our addition operator, like we have two strings x and y, and obviously that's not in this slide here, an additional third string variable z that can hold the result. Well, we obviously don't want to add the character value of h to the character value of w, then the character value of e to that of o, and so on. So what would be useful application for a plus operator for strings? So maybe it's something like concatenation. So if we add two strings together, so we write x plus y, we would expect the result to be both strings concatenated one after the other. So if we have x plus y, our result would be hello world here. And this works because we have type information. If we didn't have any information about the types here, then actually our compiler wouldn't know which machine instructions, or in this case it might be a function call, even on strings, to issue here. Obviously this example doesn't work in C, so just not to confuse you. If you have an untyped language, this gets more difficult. So an untyped language might have to provide lexically different operators for each case. So lexically different because this enables your context-free grammar to distinguish between these operators because they have different token types. For example, in BCPL, you have the regular plus operator for adding integers, and for floating points, so there was a BCPL extension for floating points, you had to use an additional operator which was called hashmark plus. So that made life quite a bit more difficult for the programmer. So one additional advantage of having a type system is that we can actually generate better code. So if we define types, then we can provide our compiler with detailed information about every expression that's contained in our program. So for example, in untyped languages, we would need to do runtime type analysis and runtime type conversion if we encounter an expression that uses types for which we don't know at compile time what they're used for. Whereas we can use static generation of correct assembly statements if we have a typed system. So if we had a runtime type checking, we would need a runtime representation for the types. So each variable not only has a value field in untyped languages, but we also need a so-called tag field, which indicates, among other things, the current type of that variable. So this is memory overhead, this is access overhead, because we have to update this, we have to check it each time we access the language. So essentially, knowing types at compile time makes it easier for the compiler to generate good, which means efficient and small code. So for example, if we have two types a, b, both an integer, then we know that our result of a plus b is also an integer, and we could generate something like in pseudo-assembler right away an add instruction that just adds two registers here, which would be integer registers, to store the result in some destination register. Now, type compatibility can be strict or not as strict. And of course, if we have numbers, we would also want to be able to add numbers of different types together and get a correct result. So if we wanted to add an int to a float, it should actually not be an error, but the compiler should be intelligent enough to know that floats have more precision than ints. So it would be intelligent to convert this int to a float first, and then add both values as float variables, getting a float variable as a result. So this is the second example in our table here. So if we add an int variable to a float variable, then we do something we call type propagation. So we need to propagate this int to a float to get a float result out of here. So we can again generate relatively efficient assembler code for this. This is now one instruction more because we have to do this conversion. So there's a pseudo instruction that might be I to f for integer to floating point, which just converts your integer number to a float, and then you can do two floating point additions here to get a new floating point result. And of course you could do the same if you add the int to a double, and then you would automatically get a double variable here, and accordingly a double addition instead of a single precision floating point addition as the result in our hypothetical machine language. So for a language where we know the types of variables and expressions only at runtime, this means that the compiler has to insert these runtime type conversions into the generated code on demand, so whenever it might be required in an expression, instead of only inserting them when it's actually required for a static type system, because the compiler would know this. So this is a hypothetical partial code just for evaluating an expression that we want to add to data types A and B, so two variables of of two different data types, or possibly even identical data types, and assign them to a third one. So if we have like only integers and reals, we would need to consider all combinations. So for example, two integers result in an integer plus a float results in a float, float plus float results in a float, double plus float should also result in a double, and so on and so forth. So we need to check the tag of our first operand first. So if this is an integer, and then the second variable here is also tagged as an integer, then we would know that we can do some addition operation, which would be an integer addition here. So we could take the values of the variables here, assign them to something which is C, and set the tag of our C to integer. But if we have an integer as our first variable here, and a real variable here as B, then we would need to convert our first integer variable to a real variable here, save that to a temporary variable, do a floating point addition here, and tag our result as a real variable. And you have to do this for all the other type combinations. And if something doesn't work, for example, you might not want to lose precision. So if you, for example, have two floating point variables and try to assign these as a result to an integer variable, you might not want this. So in this case, you can signal a type fault. Now, unfortunately, this happens only at runtime, so it's very difficult to check for this at compile time. So your users might actually complain that your application crashed because at runtime you had a weird combination of parameters that actually caused your runtime type checking system to generate a type fault. Yeah, and the right-hand side is just giving some of the other combinations. So if you have a real variable and an integer variable here, now you have to convert B to real and do the addition here, and so on and so forth. And you also have to catch all the incompatible cases here. And of course, going through all these combinations here takes quite a lot of time. Of course, you can optimize this using like bit patterns and combinations like this, or jump tables, but still, it's an overhead compared to just generating one or two single machine instructions for such an expression. So what are the components of a type system? Now, it's a bit like building mathematics from axioms. So essentially you have some very primitive base types, and these base types are usually types which are more or less directly supported by a processor. So we can have a base type for numbers, which might be integers of limited range. So for example, for a 2's complement 32-bit floating integer number, it might have values from -2 to the -31st to 2 to the 31st minus 1. You can also have approximate real numbers, so floating point numbers, which of course also have constraints in the values they can store. And very often the underlying hardware implementation has influenced the available number types. So this is especially a problem if you program in C. So you have this int variable, and an int variable doesn't have a defined size in C. The size of an int variable really depends on the machine you're using this on. And this can get really weird. So on a PDP-11, the machine Unix was first written on in C at least, an integer variable would be 16-bit. On an AVR microcontroller, which is an 8-bit microcontroller, you would expect an integer variable maybe to be 8-bit, because that's the largest amount of data the processor can handle with one instruction. But having 8-bit integers would break too much code, so the AVR GCC compiler writers actually decided, oh, let's use 16-bit integers for AVR code, which is weird. And then of course you have 32-bit integers for very common 32-bit architectures, But then again, you would expect, if you go to a 64-bit processor, that your integer would now grow to 64-bit in size. On very many machines it doesn't, but on some it does. That's strange, and this also depends on your compiler and operating system. And the reason for not extending ints to 64-bit on 64-bit machines was that it would actually break too much code out there that was developed for decades on 32-bit machines. So I think that's not a very good idea, having machine-dependent data types visible in your language. C, of course, tried to fix this, so there's a header file that's called standardint.h, which has data types, for example, for integers and so on, of specific bit widths. So, for example, we have an int 32 underline t for a 32-bit integer type. Another base type that's very common is a character. Now, characters also are not very standard, so traditionally computers could have support for 8-bit ASCII characters. Some even only had support for 7-bit ASCII characters, and some even older machines where C compilers were available even only had 6-bit characters, which is not allowed in modern C anymore, luckily. And more recently, we can have characters of larger sizes, like Unicode 16-bit encodings for international character sets and so on in Windows, or on almost all other systems we have a variable size character encoding UTF-8, which can be anything from 8 bits to 32 bits in length. So this gets more difficult. And you might also have something like booleans, which are not available originally in C but came in later. So booleans just have the values true and false, usually represented like as a bit, like 0 and 1. And then you have your special set of operators on booleans, like AND, XOR, and all the binary logic operations you're used to. Now there might also be other possible data types or base types in your type system. For example, the Lisp programming language. Lisp is one of the oldest programming languages, which was already invented in the 1950s and was very famous in the last artificial intelligence wave in the 1980s. So people actually built their own machines that contained a microprocessor that was able to execute code that was a very simple Lisp representation in hardware. And Lisp provided a recursive basic data type for lists. So essentially your Lisp, well, Lisp stands for list processing, so that makes sense. So Lisp had something in the basic language declaration that we have to implement ourselves, and we've seen this in our C crash course, for example, with quite a lot of overhead as linked lists using pointers in C, whereas in Lisp, hardware could actually do it. For other applications like signal processing, music or video applications, you might want complex numbers as a basic data type, and if you have modern accelerators or even processors with instruction set extensions for gaming or numeric processing and so on, you might have vectors or even matrices of numbers, which means you can, for example, do a vector addition all in one machine instruction, which is of course much faster than for a vector than adding all the elements of the vector one after the other. So this is mostly done here to improve the speed for certain kinds of applications, and this works for multimedia data processing, data compression, as well as for many game applications, which is fun. So in the long run, of course, these basic data types don't make you happy, so most programming languages actually allow you to define more complex data types based on these basic data types, so of a combination of these or a repetition of these, so we can have compound and constructed types. So these combinations of elements of our base type come in different ways. So for example, as arrays, so arrays group together multiple elements of the same type. This might be one of the base types or even one of the compound types we declared ourselves. So for example, an array containing 10 integers, int a of 10. Very many languages also support multidimensional arrays, which would be int a of 10 and then another dimension, which didn't fit the slide here. Another type that has different elements of multiple elements of the same type are strings, as we've seen. So some languages treat strings as compound types instead of a basic type. Most common, we've seen this in character strings, and sometimes there's also bit strings, where you can actually have sets of bits that belong together. Now, a true string in a programming language differs from an array type in a number of important ways. So true strings can have operations like concatenation, translation, and computing the lengths. And we can also compare two strings like in a lexicographical order, like we can say we have a Boolean expression and bar is less than foo would be true because bar comes earlier in the lexicon than foo. And we can also have enumerated types. Enumerated types you might know from C as enums, which give successive numbers to named elements. For example, if you want to have weekdays that you can access by names, so you can have Monday, Tuesday until Sunday here. And then you can have an enum weekday, and this enum would assign a number to each of these, starting with the lowest number, like 0, for example, for Monday, and going up to 6 for Sunday. And then you can compare days of the week, and you could compare and figure out that Monday is less than Wednesday. So if you want to combine variables of different types into a common data object, then we can use compound types here. So a compound type that is well known is a structure, which we have in C. Pascal-like languages, they're working very similar. They're just called records. So these group together multiple objects of arbitrary type, and the elements of such a structure here are then given explicit names instead of just an index like with arrays. So for example, if we had structures for a parse tree for a compiler, we could have a structure which is called node1, and this contains 3 different elements. So a pointer to a structure of the same type here, an operator here which might be an unsigned integer value, and some value of a node which might be an integer value. And we might have other nodes with a left and a right child node, which then have 2 pointers to this node 2 structure here, a left and a right pointer, and again an operator and a value. So the type of a structure here is the ordered product of the types of the individual elements that it contains. So we have something like a cross product here. So a type of a node 1 would be a node 1 pointer combined with an unsigned combined with an integer, whereas the combined type of a node 2 would be a node 2 pointer combined with another node 2 pointer combined with an unsigned combined with an integer. And these new types should have the same essential properties that base types have, because we want to be able to actually operate with variables of these new types as with variables of our base types we're accustomed to. So which other types might we have? Well, you know all about pointers here because you program in C, so you know pointers are abstract memory addresses that allow the programmer to manipulate arbitrary data structures in memory. So you can save an address and you can later examine the object at that address, even though it's no longer, for example, in the scope of your current code. And this is very often created when you create objects with new in C++ or just a heap object with a memory allocation function malloc in libc. Some languages provide an operator to return the address of an object. That's our AND operator in C here. C is very liberal with this, whereas some other languages restrict pointer assignments to equivalent types, so you don't get into trouble by trying to write an integer value to a pointer which actually points to a float variable and then just mess up the data inside of that variable. Sometimes you want this, for example, if you have raw memory access or device access to I/O devices, then you need something like raw access to bits, or you need to be able to just switch data types around because your network code accepts integers but you want to send floating points, something like this. But some languages are more strict here, so they protect from using a pointer to a type T to be applied as a reference to another type S. Some languages allow direct manipulation of pointers, so C, for example, allows arithmetic of pointers, so you can do pointer plus 4, whatever. Remember, if you do this in C, a pointer plus 4 doesn't increment the pointer by 4 bytes, but by 4 times whatever the size of the base element of your pointer is, so whatever your pointer is declared to point to. This might include auto increment and auto decrement, so that makes certain low-level hardware operations much easier to implement, but of course it's very dangerous because, well, if you do a calculation that goes wrong, you might end up reading or even overwriting, well, memory locations that you shouldn't access. But still, this would allow your program to construct new pointers, so especially when you write an operating system or something like this, this is very useful. But of course, especially if you're an inexperienced programmer, you can make so many errors. So essentially, for starters, C is probably not a very good programming language to begin with. In addition, it also makes the task of automatic program correctness checker harder, because a pointer could point to any location in memory. So if we have two pointers and we write to these two pointers and we don't know about their values, we couldn't actually know when we analyze our program statically, so our compiled program without executing it, we wouldn't know if the one write to one pointer would actually overwrite the whole or part of the memory that the other pointer points to. This is one of the biggest problems in static analysis of C programs, that you can actually must invest lots of work actually to analyze this pointer equivalence. And this frustrates a number of students. So some of my former PhD students have spent quite some months on doing this in a more optimal way. So we've already seen in our Pascal example that type equivalence is actually a difficult problem, because you need to decide between being on the complete safe side and making life for your programmer not too hard. So in general, as a language designer and compiler designer, we need to ask ourselves, when should our language actually allow assignments or operations between different types? And for this, there are two general approaches. The first approach is if we have a name equivalence. So in C, we can do something like type defs. So we can invent new type names for existing data types. So we can say we want a new type name length, but this new type name length should just be an integer, but this is another name for it. And we want an additional type name height, which is also an integer. So now we declare two variables here, a variable L of type length and a variable H of type height, which we initialize. And then we try to assign a height to a variable that is supposed to hold a length. So that might indicate a serious program error, because if you write something like a program that is built for architects to design houses or stuff like that, of course switching lengths and heights would be a severe problem here, because your house might look very funny. So obviously you might not want to allow such an assignment here. So here the programmer can select any name for a type, and if the programmer chooses different names, even if they have the same basic data type like an integer here, the language and its implementation should actually honor this. So they should actually consider that the programmer did this intentionally, assigning different names of different types here for our variables here. So this assignment should indicate that something seems to be semantically wrong with our program. On the other hand, we can have something like structural equivalence. So structural equivalence asserts that two different types are equivalent if and only if they have the same structure. That means two objects are interchangeable if they consist of the same set of fields and the same order, and those fields all have equivalent types. So this could mean we have a structure here of two integers, which we call pixel, which has two fields x and y, both are integers, and we have another structure, both again with two fields. One has a temperature, the other has humidity, and we call this weather. Now, if we have structural equivalence enabled here, we could assign a struct pixel to a variable here of struct weather, and we wouldn't complain, even if that would semantically probably not make that much sense. So we have already seen that for some applications it would be great if our compiler would automatically be able to adapt data types which are somehow compatible to each other. So it would promote an int variable to a float variable, for example. So we wouldn't have to use explicit conversions from int to float in order to write expressions that use an int and a float at the same time. And to do this, we use inference rules. So inference rules specify for each of the operators here a mapping between operand types and the result type of this operation. So for some cases, this mapping is very simple. For example, if we have an assignment which has one operand and one result, so x equals y, then we know that the left-hand side, so the variable we assign to, must have a type that's compatible with whatever is on the right-hand side. So it might be constant or another variable of a certain type. Very often, the relationship between operand types and result types is specified as a recursive function, on the type of the expression tree that we have generated in our parser here. So the result type of such an operation is a function of the type of its operands, and this can be, for example, specified simply using a table like that one here. So we can say if we add two integers, we've seen examples for this before, we obtain an integer. If we add an int and a float, we promote this and get a float. An integer plus a double gets a double. A float plus a double should not lose precision, so we get a double, and so on and so forth. So very many compilers recognize certain combinations of these mixed type expressions, especially for numerical expressions here, and then automatically insert the appropriate conversions as we've seen before, because this makes life easier for the programmer. So which tools could we use in order to implement a type system inside of our compiler? We've already seen that implementing this as part of our parser for context-free language isn't possible, because that would remove the context-freeness of our language, and implementing a parser for a context-sensitive language is very much overhead, so we shouldn't do it. So what we do is actually we declare all these type system parameters separately, and we can also do it in form of a grammar. So we have a separate grammar we call an attribute grammar. So an attribute grammar again is a context-free grammar, but it's separate from the grammar of your programming language itself. So it's a context-free grammar that we augment now with a set of rules, and each symbol in the derivation or parse tree has a set of named values or attributes. And the rules in that grammar here that we added to our context-free grammar specify how to compute a value for each attribute. So these attribution rules are functional, so that means they uniquely define the value that we get. So we have an example context-free grammar here, which goes from a number to a sign or list. A sign can be a plus or minus, and a list can be a list and a bit at the end, or just a single bit, and a bit can obviously be a 0 or a 1. And this grammar would describe something like signed binary numbers. Yeah, that's an invention, obviously. So we have plus 101, which would be plus 5, or we could have minus 11, which would be something like minus 3. Obviously, you know, binary numbers are usually encoded differently, like for example using 2's complement. But let's just use this as a simple example. And now let's just try to augment our context-free grammar with rules that actually allow us to compute the decimal value for each of our valid input strings that the language that is generated or detected by our grammar actually supports. So we have an example here. So for minus 1, so the binary string minus 1, we'd go from number to sign list to sign bit. Then a bit is 1 and our sign is minus. So we have the parse tree like this. So we have number on top here as our start node here, and then we have our two parts here. So we go to the left for sign and resolve the sign to the minus token here, and we go to the right for bit and resolve our bit finally over an intermediate step of a list to the bit which has the token 1. And we can do the same for a longer binary string, obviously, which means we have the same on the left hand side, and we have to recurse through a number of invocations of list here until we arrive at our leaves in the tree here, so we can represent our binary string 101 and our sign minus here as the parse tree. So that's nothing new, you've all seen this before. So to build an attribute grammar from this context-free grammar, we now add rules to compute the decimal value of a signed binary number. So for each of our productions here, we have attribution rules that can execute arbitrary functionality. So for example, when we start, we are at the top of our tree, we would set our list position to 0, and then we recurse into sign and to list. So if our sign would indicate it was a negative number, so we had a minus sign, then we would use our right hand side result here. So our number value would actually be assigned the value of whatever comes out of our list, prepended by a minus sign, so multiplied by minus 1. So if sign negative was not given, so if the sign was positive, then the value we return from our grammar would just be the value of our list on the right hand side, so recursing down our bits. So if we go down our productions here for sign, we just check if we see a token plus, then we set the result return code and indicate that negative is false, so we have a positive number, and if we see a minus, we set that negative is true, so we have a negative number. Now for list, we have to do a recursion here. So what we do here, we implement list 0 and list 1 on the left and right hand side. Still, they refer to the same non-terminal symbol here, but they're used to actually indicate the left and right hand side of assignments here. So for example, if we have a production like this here, we know, okay, we have a bit at the end and we get another element on the left hand side. So our position we are constructing, so our binary string add is added to this position is we added 1, so we increment this position here. We store the position of the list here we have, and we take the value. From the value we actually read from that bit here, plus whatever we had already in the list before. If we only read a single bit here, well, we get the position from the list, and the list value is actually assigned our bit value. And finally, when we have our bit here, if we read a 0, well, we don't need to add anything. But since we now kept a trace here of the current position in our list, which means the number of the bit that we're actually constructing in our binary string or recognizing in our binary string here, this would mean if we recognize a 1, we don't return a 1, but we return a power of 2, which is exactly the power of 2 for the bit position where this 1 shows up. So if it shows up on the rightmost bit, for example, then we would return 2 to the power of 0 or 1, and then for bits further to the left we would return 2, 4, 8, and so on and so forth. So each symbol now has attributes which contain values that can be returned when the production is resolved for this symbol. So number has a value attribute, which would be an integer number, positive or negative. Sign only has an indicator if the sign that we passed was negative or not. A list has 2 attributes. It has a position here, so it keeps track of the bit it's currently reading, and a value, so it keeps track of the value that was at the moment accumulated, but this might still be incremented by additional bits coming in other positions here. And finally, a bit also has a position and a value, and this value is always a power of 2. So this would be our syntax tree for example 1 with added rules for our attributes here. So for -1 we would go down from number to sign. Sign would read our minus token, so the return attribute of sign would be neg, and the negative is true because we have a negative number here, so this would be handed to number here. On the other hand, we must go down to list. Okay, when we do this for the first time, we initialize our list position to 0, and then finally we go down to our bit. We know our bit position is 0, so our bit value is 2 to the power of 0, which is equal to 1. So we return 0 as pos, value as 1, go up here, and then can finally return this information up to our number, and our number can then return its value -1. And this is one of the possible evaluation orders here. This is one I just described, but there can be other orders, so we could just go down the right hand side of our tree first, and then the left hand side second, which would hopefully lead to the same result. So the evaluation order must be obviously consistent with the attribute dependence graph. So Donald Knuth suggested a data flow model for evaluation, so if you're interested in details on this, I'd like to refer you to this paper here, which means that first you should actually evaluate the independent attributes, and after that you should evaluate the other attributes in the order that your input values actually become available. So for our example -101, for our second example, this gets a bit more complex. So left hand side is identical, we just see a negative sign here, and then the right hand side we see that our list position now increases from 0, we read a bit at position 0, to 1, we read a bit at position 1, which is 0, so we don't care. And finally, and here it gets interesting, we also read a bit at position 2, so the leftmost bit directly after the minus sign, so the one here. And for this, we know there's a position 2. We have passed this information to bit. This bit has read a 1 as a token, so it means it needs to return 2 to the power of plus, so 2 to the second power, 2 squared, or 4 as a value here. So it returns 4 here. It adds this to the value obtained by this bit, which is 0, so we still have 4 as a value here. And finally, we get to the rightmost bit, which has just handed its value up here to our topmost list node here. So this value was 2 to the power of 0, or just 1. So we add 4 coming from the left hand side and 1 coming from the right hand side. This gives us 5, and we add this, we pass this up to number. Number combines this with the indication that the sign was negative and returns minus 5. So this is a simple example, but this is the complete attribute dependence graph for our input minus 101. So this means it shows the flow of all attribute values in our example. And we've seen, if you look at the arrows in this diagram here, the pink ones, that some information, some attributes flow downward here, like our position here, whereas somewhat, so these are so-called inherited attributes. So bit inherits the position attribute from list, for example, whereas other attributes flow upward, like the value from a bit to a list. So this is a so-called synthesized attribute. And any rule can use attributes in the parent, children, or even in the siblings of a node here. So this makes attribute grammars more flexible. And you see it's just a second overlay of all of this, which is actually not that much dependent on your context-free grammar anymore. So what you have are attributes associated with nodes and parse trees, and the rules are value assignments associated with productions. An attribute is usually defined once using some local information in your node, and when you want to apply the rules, you should label identical terms in the production for uniqueness. And the rules, together with the parse tree, define this attribute dependence graph. And what's important is that this graph must be non-circular, because if you had circles in such a graph, you would have to have an endless iteration or recursion going through your graph to obtain a value. So this would mean even though you can successfully parse the context-free expression, your type analysis would never terminate, and of course that's problematic. So all of this together produces a high-level functional specification, and as we've seen, we have these two types of attributes, these synthesized attributes, which depend on values from the children in a given node, whereas our inherited attributes depends on values from the parents or even from sibling nodes in our est. So the attribute dependence graph is a specification for the computation. It's not an algorithm in itself. So how do we use attribute grammars now? So an attribute grammar can specify context-sensitive actions, because it can take values from syntax, it can perform computations with values, something our regular context-free grammar wasn't able to do, and we can also do additional things like we could insert tests, we can insert logic. And you may remember our description of YAC. So in YAC, after each rule describing some part of our grammar here, you could insert actions. And these actions, obviously, in these actions you're free to do many things. And you can imagine that the implementation of your attribute grammars would just be a part of these functionality implemented in C that you actually append to a part of your grammar in YAC. So for synthesized attributes, as we've seen, we use the values from children and constants. We can have S-attributed grammars, and we can evaluate them in a single bottom-up parse. And this is a very good match to LR parsing, whereas inherited attributes use values from the parent, maybe constants even, and values from siblings. So inherited attributes directly express context here, something which is not possible just using our grammar. Now inherited attributes make life a bit more difficult, so we can try to rewrite them to avoid them, but they're thought to be more natural, but it's not that easy to work with inherited attributes at parse time. Nevertheless, we want to use both kinds of attributes to be as flexible as possible, if this is somehow feasible. So how could we evaluate such information that we've obtained? So there's different approaches. The first one is a dynamic dependence-based method, which means you first build the parse tree and the dependence graph, and then you topologically sort the dependence graph and try to define the attributes in topological order. There's other approaches, and the next approach to discuss here are rule-based methods, or also called just a tree walk. So for rule-based methods, you analyze the rules at compiler generation time and determine a fixed static ordering, and then always evaluate the nodes in that order. And there are additional methods which are oblivious, so they can be implemented in different passes of your compiler or in a data flow analysis, which means you just ignore the rules and the parse tree and just pick any convenient order at design time and just use it. So you're very flexible. So this attribute grammar representation is a very general way to enable you to realize type systems in your compiler. So let's go back to our second example for -101. And we've already seen this is our syntax tree here, which we constructed. So if we add the attributes here, we get all the information of synthesized and inherited attributes, like the position, which was inherited down here, the value, which was synthesized up here, using these both two together, so value 4 and value 1. These sibling node information was combined here in this list element, so they were just added together to give a value of 5, and so on. So this is our attributed syntax tree for our general context-free syntax tree that we've seen in the previous slide. So now we can add this information again to indicate the inheritance of attributes. So our position is inherited down from list to recursive list invocations, and also from lists to single bits. And we can also have synthesized attributes. So we can say we have a token 1, which synthesizes the value attribute in our bit, and then we can synthesize something like a value 5 here, which could be combined from this value 4 and value 1. So these are the other synthesized attributes that also occur in our annotated grammar here. So this is all that happens. We've seen this picture before. So let's just try to show the computation that happens here on the attributes, and just remove the syntax tree. Whoops. So this is what's left here. So this is the attribute dependence graph on its own without any syntactical structure here. And this actually doesn't represent the structure of your program, but this represents the flow of values in this specific instance of your program. So for example, in this number -101, we've parsed here as a simple example. So we know that this value 1 propagates to here, and because it's a 1, we know this value 2 for our position propagates to this value that's returned, because we take the second power of 2, then we pass this value upwards here. We do the same for this bit here. Here it's 0, and the same for that one here. And then we combine those, so we can add those together here and can add the values returned by this bit and this list together, but we don't have bits and lists anymore. So we're only considering the flow of values upwards and downwards in this attribute dependence graph and how they are combined. So the dynamic mode methods to analyze type systems now sort this graph to find values that are independent and then work along the graph edges. If we apply rule-based methods, they try to discover good orders by analyzing the rules. And the oblivious methods just ignore the structure of this graph, so they just work with the values here. And we've already said that circles in such a graph are a difficult problem. So we can only evaluate acyclic instances of our attribute graph here, because if we had a circle here to evaluate it, we would go round and around our circle and we wouldn't know when to end. Now the problem is, if we have large attribute graphs, this general testing for circles in graphs is inherently exponential, so it's very expensive. So what is done usually is that one tries to prove that some grammars can only generate instances with acyclic dependence graphs. There are several classes for this. The largest such class is called the class of strongly non-circular grammars, or SNC, and for these it can be proved that they can be tested in polynomial time. But failing an SNC test doesn't mean you have a cycle, but just if you pass the SNC test, you know you don't have a cycle, which is already something you want to know. We don't go into too much detail on this, but still what's interesting to see is that grammars also have an additional dimension of circularity, which comes into play here, which is important. Many of the evaluation methods that are actually applied in practice just try to discover this circularity in a graph dynamically, but this might be a bad property for a compiler to have, because that then means our compiler runtime might depend on the structure of your program, which is not exactly what you want. So what would such a circular attribute grammar look like? Now we have one here, and let's say we add a number of attributes here, A, B, C, and we have relations here. So again, we have list of A to 0 when we just read numbers and signs as before. Or read our list, we increment our element A, our attribute A, by 1. We assign the right hand to the left hand side attribute, and we finally increment our value by our bit value. And if we read a single bit, then we add these together here, and for bits we do the same as before. Now the circularity that actually happens is somewhere here. Let's take a look at this in detail. What's important to know, there is no circularity in our context-free grammar describing the structure of a language. The circularity is only contained in our attribution rules and not the underlying control flow graph. So let's take a look at the example for this circular grammar. So again, we have our example -101. So we start and we choose the first attribution rule when we go down a list here and set list attribute A to 0. Then we continue to dig down the list. So we set list 1A to list 0A plus 1. So we go down here. Then we inherit the element the other way around. So list 1 point B is assigned upwards. So we synthesize this attribute upwards in our graph to list 0 point B. And finally, we have list 1 point C is list 1 point B plus bit value. So essentially, we add this element and that element here together. Now maybe you already see where the problem is, but let's take a look to see if we can find this in a bit more drastic way. And here it hides. So the cycle is here. So essentially we have a dependency of the attribute B of a list element at a certain level in our graph to the element C, and the other way around. Element C also depends on the value of element B. So here is a circle in our attribute graph, and if we try to evaluate this, well, we would never break this circle because we would evaluate this condition here over and over again. And of course this is problematic and we need to avoid this. So to show it in detail on the right hand side, this is exactly the cycle that happens. So we have list 0C and list 0B here on the left hand side, whereas we have list 1B and list 1C here. And if we combine this here, we get into that situation, which means we can't get out of the evaluation without breaking something. So circular grammars have indeterminate values, and our algorithmic evaluators will fail if we have a circular grammar because, well, our evaluation will probably never end. Whereas non-circular grammars, for these we know they evaluate to a unique set of values, but still circular grammars might give rise to a non-circular instance of a grammar, but I wouldn't bet the correctness of my compiler on it. So this is a deep graph theoretical problem that needs to be solved here. So undoubtedly you should probably use grammars that are provably non-circular. Now we're not discussing how to prove the circularity of grammar here. That goes into too much detail for an introductory compiler lecture, but you should at least know that problems like these exist. Now remember, what we're doing here is we're studying these attribute grammars to gain insight. So we should actually, of course, avoid circular indeterminate computations because, well, then essentially this would also happen in the generated code if we would allow this. So if we stick to these provably non-circular schemes, the evaluation of our expressions and the attribute grammar should be easier. So one thing we can do as an example for an extended attribute grammar is to estimate cycle counts. We've seen this before. We've seen the cost of operations in a very early example for grammars. Now let's see how we can do this with an attribute grammar. So each operation has a cost, and if we have costs for basic operations, we add them bottom up if we combine parts into an expression here, and finally into an assignment. We assume one load per value here, and we assume that registers or values are not reused. And this is a very simple problem to solve for an attribute grammar. Now this could be a grammar for a so-called basic block. So what's a basic block? So let's take a quick look at this. So a basic block is a special, very simple structure that is part of a program. So for code in a basic block, you have a number of restrictions. So code in a basic block has only one entry point at its start. So when you jump to that basic point, the only point you can jump to is to its very first instruction. So that means no code inside of the block is a destination of a jump instruction, neither from inside of the block, nor from anywhere outside of the block, so anywhere else inside of your program. In addition, your basic block has one defined exit point, so only the last instruction of a basic block can cause the program to begin executing code in a different basic block. Or in simple terms, this means whenever you know the first instruction in a basic block is executed, then you know the remaining instructions of your basic block are executed exactly once in that order until you leave the basic block at the exit point. So if we have source code like this here in a hypothetical C-like language here, we have three variables which we initialize with values here. We have a while loop, and then we have an if condition inside of that, and we have returns. So now we need to think about what our computer has to do when it would implement a program like this. So for a while loop, you obviously have to jump. So if this condition is fulfilled, you jump inside of your while loop, whereas if k is 100 or larger, you would jump over the body of your loop to return. And you would do similar for if. So if j is less than 20, you would jump into that block here. And when you're at the end of that block, you would jump over it and start your while loop again. Whereas if j was equal or larger than 0, you would jump over that block here, jump into the else block here, and then finally jump up to the start of the loop. And that helps us to identify exactly our basic blocks in our program here. So our first three instructions, they don't jump anywhere, we don't jump inside of these, so they're part of a single basic block, which we just call B1. Now our while loop is a jump target, because we jump to the beginning of a while loop when we're at the end of a while loop. So we know at that while loop here, a new basic block must start. And it immediately ends after our while instruction, because our while instruction can choose to either go inside of your loop body when the condition is fulfilled, or to jump over its loop body to whatever comes behind it. So since we jump out of here, we have one defined exit point here. So this while is a basic block on its own. And the same happens for if, because if can either continue running into here, or it can jump over here. So this is its own third basic block here. So the next two instructions are just expressions, so just expressions that are assigned to variables here, so they form a basic block, we don't jump anywhere. Then we have the else, so we would jump at the end of this basic block over here, and then jump up here again. So j equals k, and the next instruction k equals k plus 2 are yet another basic block, b5. Then our loop ends, because there's no code actually executed here, so we don't model a go-to to the beginning of a while loop here in our basic block. This is implicit. So finally, what's left is the last location that is jumped to. This is our return instruction, and this is always jumped to when our while loop condition is no longer fulfilled. So then we jump down here, so return j would form our sixth basic block. And it doesn't really matter if our code is here like a source code representation or assembly code or some other intermediate representation. Basic blocks always have that meaning that they indicate a sequence of instructions with no change of control flow in between. So just a linear sequence of instructions where you always have one entry point at the beginning and one defined exit point. So now we could extend our grammar for such a basic block which just has a number of expressions one after the other, so no whiles, no ifs, and so on. And we can extend this now with an attribute grammar for costs. So we would start down here with our terminal symbols for number and items. So for example, if we have a number here, this would be just a numerical number like 23. So we would need to figure out the cost of loading this immediate value into a register here, whereas when we have an identifier, this is a variable here, so we need to figure out the cost of loading this variable from memory into a register, and then we synthesize this cost attribute for our factor here. If we have something in brackets, it doesn't add anything to our cost because this is just a structural representation. So this means if we have an expression here, and this is in round brackets here, and this gives us a factor here, this means that we just copy the cost of the expression to the cost of that related factor here. Now if we have arithmetic expressions here, so our four basic arithmetic operators, plus, minus, multiply, and divide, we, as we've seen already in the previous lecture, recurse down our left and right hand side non-terminal symbols. We obtain these synthesized attributes for cost from walking down the tree and walking back up again. So for example, for our division here, we would have the cost of our left hand side of our division, we would get the cost of our right hand side of our division here, plus we need to add the cost of a division instruction, so dividing these two intermediate values here, and we do the same for multiplying, for subtraction and addition obviously. If an expression just resolves to a single term, there's no additional computation involved, so this just copies over our synthesized attribute from term to expression again. And finally, when we have an assignment here, so assignment means we need to store the value of the expression into that variable here that's indicated on the left hand side. We just obtain the cost of our complete right hand side expression here and add the cost of a store to memory to it. And so finally, when we have the cost of an assign, then we just copy that cost of that complete assignment plus a potentially long expression to our block. And since our block is a basic block, so it can consist of one or more assignments plus arithmetical expressions, we increment the cost for that complete block by the cost for, that we determined for each individual assignment that our basic block consists of. So what are the properties of our example grammar? Now in this example grammar, all attributes are synthesized, so this is a so-called S-attributed grammar, so S for synthesized. So all the rules can be evaluated bottom-up in a single pass, and this is obviously a very good fit for a bottom-up, so a shift-reduce parser. This is a solution we can understand easily, and it seems to fit the problem very well. Now, can we improve this somehow? Yeah, we can, for example, imagine that we load the values of variables. So if we reuse a value on the right hand side only once per block, so we save memory loads, so we don't need to load a value at each use of that variable here. And this means we need to track which values have already been loaded into registers in the same basic block. So we can do this like this. So this is a better execution model. This load tracking adds complexity, but most of it is in the what we call copy rules. So there's the rules that copy over a synthesized attribute to a different level. So now every production needs rules to copy before and after. So essentially we have additional rules with before and after, and then we copy this up our tree. And now we need to check if we encounter an identifier, and we haven't seen this before, this identifier, then we need to add the cost of a load, and then actually add the element of our name of the identifier to, and the previously read identifiers to the identifier set that is seen after we've seen this factor, and otherwise we just have a cost of 0 because we know this identifier, this variable, is already contained in a register, so we just copy the before set of identifier we've seen to the after set because nothing has changed. So This makes our attribute a bit more complex because now we have set operations here. So we have a set of identifiers here. So we have to add identifiers to a set in case we load them. And we load them because we haven't seen them before. But essentially that's all the changes we have to do to our grammar. So you see these changed rules here in order to make this optimization and to estimate this more precisely to enable that we only load a variable when it's not already contained in a register inside of this basic block. So adding this load tracking now requires us to set before and after for each production, and this must be initialized, this must be updated, and it must be passed around the tree. So essentially for each of the expressions now we have to add this before set for expression here and for term, and then we have to finally determine the after set here for the expression. And the problem is that when you do it for all the expressions in your grammar, these copy rules spread wildly throughout your grammar, so they multiply rapidly. Each creates an instance of the set, so set operations are pretty costly compared to arithmetic operations. So this involves lots of work, this costs lots of space, and you have to write lots of rules, which is something you probably would want to avoid, because the more rules you write, the more errors you can make. But still, can we do it even in a better way? So the problem here is that for a very long basic block, we would run into the problem of running out of registers. So we only load a value into a register when it has not been loaded before. But what actually happens when we load more values than we have registers available? Then we would have to spill registers out to memory again in order not to overwrite a value we would need afterwards. So can we account for finite register sets here? Well, this would mean before and after must be of limited size, so they only can hold, for example, like 32 elements if you have 32 general purpose registers. This would add complexity to this factor rule that goes to identifier, and would also require more complex initialization. So going from these tracking loads to tracking registers is just a small change because the copy rules are already in place. We would just need some additional local code to perform this allocation. So we don't go into too much detail here. It's a nice exercise for you if you're interested in these attribute grammars to try to figure out how to do this for a restricted register set. So essentially you would need to track loads now. So we've introduced before and after sets to record loads. We have added more than 2 copy rules, or at least 2 copy rules per production. We have a serialized evaluation into the execution order, and for tracking loads we made the whole attribute grammar then large and cumbersome, and for the finite register sets we have complicated only one additional production from factor to identifier. We would need a little fancier in it, and the changes are quite limited. So another question we should ask ourselves, why is this one change for tracking loads actually pretty hard and the other one relatively easy? As I said, these are advanced topics, so we don't go into too much detail on this, but if you're interested, feel free to think about it and let me know what you think. So, summing it up, we see that non-local computation needs lots of supporting rules, whereas complex local computation was relatively easy. What are the problems with our attribute grammars here? Now these copy rules increase the, what we call a cognitive overhead, let's say, for the programmer who designs these rules. They increase the space requirements because we need copies of attributes. We could use pointers to reuse attributes, but this would cause more cognitive overhead because then we would need to keep track of our pointer values here. Nevertheless, the result of doing this is an attributed tree, so we must nevertheless first start building our parse tree, and then we can, if we have the attributed grammar, search the trees for answers or try to copy them to the root. In practice, even though these solutions here for simple examples seem very straightforward, in practice very many compilers actually use ad hoc solutions for this. So see the previous lecture for something on this, on ad hoc solutions, because really writing very complex attribute grammars is a nice theoretical exercise and people are doing it in academia, but it's really a nuisance if you try to do it in a real world production compiler. So I know many colleagues like to spend lots of time on type system theory, and horrible, from my point of view, ways to formalize type systems and all of this. This is all important, especially if you want to do formal verification, but this is going too far for an introductory compiler construction course. So let's rather continue with more interesting things, because we have the second half of our compiler still in front of us. So now we step from our syntactic and semantic analysis to actually generating the intermediate code we've talked about so many times already. So what can we actually generate to interface the front end of our compiler, which we now have built, including scanner, parser, semantic analysis, to the back end of our compiler, which has very interesting points like not only code generation, but especially optimization of code to make it run, for example, faster or more energy efficient. So in our next lecture, we'll take a look at 3 address code and various ways to represent intermediate representations for compilers. So here are a number of additional references about typed assemblies. So there was a hype on this a couple of years ago, like 20 years ago. There was a critique of Pascal by Brian Kernighan, whom you might recognize as one of the people behind C and Unix. And then, of course, there's another paper by Niklaus Wirth, which is Pascal as a subset and its implementation. And this paper, as you see, is 60 pages long. And this is 60 pages long because the complete source code for the compiler written in Pascal was included in that paper. So you actually have a complete subset of Pascal's simple compiler just included in a scientific paper, which is part of a book. So I bought this book from a reseller here because you can't buy it new anymore. If you love to take a look at that, feel free, and I can borrow you this book. The attribute grammar problem was described by Don Knuth already 30 years ago, and there are a number of papers on automatic generation of efficient evaluators for attribute grammar, so this is more on the theoretical side, and this is one example for this. And you see, people already thought about problems like this, like almost 45 years ago. So we're talking still about things people know for a long time, but nevertheless, these are the basics. Compilers are a relatively old and well-known topic in computer science, but they're still absolutely relevant, especially for being able to exploit all our modern hardware, which is exceedingly parallel, heterogeneous, and needs to be, for example, energy efficient and power efficient. And these challenges are mostly part of the backend, and we'll take an intensive look at compiler backends and the related intermediate representation in the rest of this course. So that's all for today. Thanks for listening, and until next time.